All right, this is the pre-video for section 4.3 and 4.4, finding real and complex zeros of polynomial functions. The objectives are to factor a polynomial into linear and irreducible quadratic factors over the real numbers, and then learn how to factor a polynomial into linear-only factors over the complex numbers. So we'll discuss what that means in just a second. So there's this theorem called the fundamental theorem of algebra, which funnily enough, we had to almost go through half of our whole textbook to get to. But it says if a polynomial f of x has a positive degree and complex coefficients, so coefficients that are complex numbers, they can be real numbers or they could even be square roots or imaginary numbers, then f of x will have at least one complex zero. Remember, a zero is something that when you plug it into the function, it equals 0 overall. The complete factorization theorem for polynomials says that if f of x is a polynomial of degree n greater than 0, so x to the first power or x to the second, x to the third, any of those being your degree, then there exist n complex numbers. So whatever your degree is, if your degree is 5, you should have 5 complex solutions such that you can factor this into what we call linear factors. Linear factors mean that each factor is only an x to the first power. Okay. Now, earlier it did say irreducible quadratics. That's if you're only using real numbers. So if you're factoring with the real numbers, you should be able to get down to linear, which is x to the first, and some quadratics that don't factor, so x to the second. But if you use complex numbers, you should be able to factor all the way down to x to the first for every single factor. So here are some examples of what some complete factorizations look like. Here's a polynomial that has some imaginary and real number coefficients. And when they factored it, notice it had a factor that was imaginary. Here's another one. And again, we're not factoring these. We're just showing you what some of them could look like. Sometimes when you factor it, you'll have these imaginary complex numbers, a plus bi, that are in your factors. And then here's one that factors over just real numbers. So what we're going to show you, and we're going to do some easy ones, is just how to break it down, first of all, using real numbers only, and then we'll do one with all complex and real numbers. So you can have at most the number of your degree different complex zeros. All right, so let's look at this first example. It says express f of x equals x to the 5th minus 4x to the 4th plus 13x cubed as a product of linear factors and find zeros of f of x. So this one, it says we should be able to break it all the way down to linears. All right, so the first thing I would do is notice that I can pull out a x to the 3rd. So that would leave me with x squared minus 4x plus 13. We would then ask if we can factor that again. Well, factors of 13 are 1 and 13, so it looks like we can't factor that using our typical means. So one way you could try to factor it is to use quadratic formula. So x equals negative b, so that'd be 4, plus or minus square root. B squared would be 16 minus 4ac all over 2a. So this would be 4 plus or minus square root. That's 16 minus 52 all over 2. So let's do 16 minus 52. And 16 minus 52 is negative 36 under the radical. And that's going to be a 6i. So 4 plus or minus 6i over 2, which reduces down to 2 plus or minus 3i. Okay, so that's how this is going to break down. So we need to look at this as f of x equals. Typically, if you just have an x out front, we like to emphasize what that answer is. X equals 0 when it's 0. So x minus 0 cubed. So notice this is still a linear factor. We're just saying that it repeats 3 times. And then we have these two zeros. When you write them, you have to imagine, so anytime you have a factor, so just as a reminder, if this is your factor, to find the root, you set that equal to 0 and you solve it. So notice it's opposite signs. So when we move these over, they're going to be opposite signs. So this is the zeros that we got. We're 0 for the x cubed, and then we have a 2 plus 3i and a 2 minus 3i. Those are our zeros. So when we write them as factors, you do opposite signs. So minus 2 minus 3i and x minus 2 plus 3i. So that's how you write complex factors. You just change the signs as you move them over. So there's my factored form, and there are my zeros. And that leads into a discussion of this next piece. Notice that these two imaginary solutions that we got, these complex solutions, they were conjugates of each other. That will always happen. If you have a solution to a polynomial function, they come in, if it's an imaginary solution or a complex solution, its conjugate will also always be a solution. So that's this theorem. If a polynomial f of x has degree n greater than 1, so it has to have at least one answer, or more than one answer, and it has real coefficients, and if a plus bi, with b not being 0, is a complex 0 of f of x, then the conjugate is also a 0 of f of x. So that's kind of like 2 for 1. If you get, 3 plus 5i as an answer, then 3 minus 5i as an answer. And a corollary to this, that just means a follow-up on a theorem. A polynomial f of odd degree with real coefficients has at least one real 0. So if you have an odd degree polynomial, there's no way that all the answers are imaginary, because the imaginaries come in pairs. So an odd degree polynomial will have at least one real number for an answer. All right, so let's look at, this is the last one in the pre-video. We want to break this down into linear and quadratics with real coefficients that are irreducible over the reals. So that means we won't use the quadratic formula to keep factoring it. And then we'll break it down into linear, which means we'll break it all the way down. So it looks like on this one, I want to try to do factor by grouping. So x to the 5th minus 4x to the 3rd plus x squared minus 4. We can pull an x to the 3rd out of the first pair. That would leave me with x squared minus 4. I can pull a positive 1 out of the second pair. That would also leave me with x squared minus 4. Then I would have x squared minus 4 comes to the front, and x to the 3rd plus 1 would be at the end. This factors using perfect squares, so that'd be x plus 2, x minus 2. And this is actually perfect cubes. So remember, perfect cubes factor into a binomial and a trinomial, and we had a pattern for that. So the binomial is the cubed root of both of these and then the sign of the original, so x plus 1. The trinomial is when you did the pairs. So the cubed root of this was x, so x times itself is x squared. In the middle, it's the two roots times each other, which would just be a 1x, or just an x. And then the cubed root of 1 was 1, times itself would be 1. And then remember, so same as the original, opposite to the original, always positive. Now, if you know anything about perfect cubes, which we do know a little bit since we've factored them, we realize that the trinomial never factors using nice factors. So this is as far as we can go using real numbers only, because if this factors, it's typically going to be imaginary or something nasty. So we're going to try to factor it completely, which means only using linear polynomials. That means x to the first, not x to the second. And to do that, we need to use the quadratic formula on that last part. So that's x equals negative b plus or minus square root. B squared is going to be 1 still minus 4ac all over 2a. So this is 1 plus or minus the square root of negative 3 all over 2. I'm running out of room down here. So that would be 1/2 plus or minus square root of 3 over 2i if we split it up into the two pieces. So when we go to write our factors, we'd still have our x plus 2, our x minus 2, we'd have our x plus 1, we'd have x minus 1/2 minus square root of 3 over 2i, and we'd also have x minus 1/2 plus square root of 3 over 2i. That's where, remember, we change the signs of these as we write them with the x. Some people don't like it this way. I've seen a variation. I'm okay with this. This is fine with me. But because there's a fraction involved in those last two parts, there's a way to fix that. You bring down everything else, And what happens is you kind of multiply through by whatever's in that denominator. So if you multiply it, you get 2x minus 1 minus square root of 3i, and 2x minus 1 plus square root of 3i. So this is also a variation of that. Okay, and that's it for the pre-video. We're not going to really test on this, breaking these all the way down like this. This is kind of just an introduction to factoring that has something that's not just real numbers, so that when we do the main pieces in class that you'll see that this is just, sometimes you get funny factors. All right, and that's the only pre-video, so I will see you guys in class tomorrow.